So now what we would like to do is to look at the next step of the aspect. So we would like to look at some of the properties of the Z transform, and then how they can be helpful for us in applying the Z transform, and also how they will help us in computing the inverse Z transform. So what are the first things that we are going to be looking at is there are three sequences: x of n with a ROC with the transform x of z, R of x as ROC. Second one is x1 of n with a z transform x1 of z, Rx1. You can also write it as R1 if you want to just make it a little simpler. Here it is x2 of n, x2 of z is the z transform, the ROC is R2. Okay, easy for us to look at that. Now, definition of the Z transform: x of z is equal to summation n equal to minus infinity to infinity x of n z power minus n. Now, if I scale this by a factor a, notice that my sequence will also going to get scaled by an alpha a. So any sort of linear scaling is going to reflect in the scaling of the Z transform, and on top of that, because of the way the Z transform is defined, exactly like the DTFT, if you add two sequences. So for example, if you have summation n equal to minus infinity to infinity x1 of n plus x2 of n. Let's say you had this combination and you are computing the Z transform. You can of course expand it and write it as x1 of z plus x2 of z. Okay, and if you will scale x1 by a, x2 by b, doesn't matter. So this is what is called the property of the linearity of the Z transform. So we are talking about a class of linear transformations. The Fourier transform is a linear transformation, Laplace is linear, the Z transform is also linear. So what can you do with the linear transformation? You can scale. You can add two sequences. You will get the output with the Z, the transform will be a sum of the transform. So the property of linearity is very important because it gives you superposition, it gives you scaling, and so basically the combination of the two, just like we did for the DTFT, will give us some very useful and interesting applications. So and because you are adding two Z transforms and the final expression has got both x1 and x2, remember both of them should exist. So therefore the ROC will be the intersection of Rx1 and Rx2. Okay, because both of them should exist, only then the Z transform is meaningful. Now if you remember, when we did the partial fraction expansion and then computed the Z transform, what were we implicitly utilizing? We were implicitly utilizing the linearity property. Linearity property. Okay, because we said that if I have a sum of three terms, I can look at them, each of them, as individual terms. So what we said was, we said that A1 divided by 1 minus A naught Z inverse. Let's call this as A1 itself. Okay, there was a term which is, this is A1, a second term A2 1 minus A2 Z inverse, A3 1 minus A3 Z inverse. We eventually related this to A1 power n u of n. We related this to A2 power n u of n. Again, I'm assuming all of them are right-sided, but otherwise you can still get the corresponding expressions. This will be A3 power n u of n. Okay, these three terms added together in the time domain produce for us the sum of their corresponding Z transform. So in a sense, the partial fraction expansion actually is a usage of the property of linearity of the Z transform. We did not explicitly call that, but we said that that is how. And if this one has got ROC1, this has ROC2, this has ROC3, property of linearity says that this final expression will have an ROC which is equal to ROC1 intersection ROC2 intersection ROC3. Okay, so basically all three of them, all three terms should exist. Okay, and another example that we had also looked at, we said x of n equal to r naught power n sine omega naught n times u of n. Okay, remember we split this as two terms, 1 by 2j, 1 by 2j r naught power n e power j omega naught n minus r naught power n e power minus j omega naught n times u of n, and then we computed the Z transforms individually. So that is exactly an application of the property of linearity. Property of linearity of the Z transform. Very, very powerful, because what we are saying is we can add sequences in the time domain and compute the Z transform by computing the Z transform of each of these sequences and putting them together. That's the property of linearity. Only thing to remember, the ROC will be the intersection of all of the ROCs, and that, so again, the property of linearity is something that we have used quite extensively. Okay, another place where we use the property of linearity was the last example that we looked at just now. Okay, x of n is equal to a power n, n greater than or equal to 0, less than or equal to n minus 1, equal to 0 otherwise. Okay, and so what we said was this can be written as a power n u of n minus u of n minus n. Take a minute to visualize. The first unit step starts at n equal to 0. The second unit step starts at n equal to n. So when you subtract these two, what will be left with only those samples between n equal to 0 and n equal to n minus 1. Okay, so this expression can be written as a of n u of n minus a of n u of n minus n. Okay, and what we can then do is if this is x of n, this is x of n, then we can say that x of z is equal to z transform of a of n u of n minus the z transform of a of n u of n, u of n minus n. Okay, z transform of that, and this is what we will like to compute, and then look at the ROC, get the intersection of the two ROCs, and all of that will have to be done. Okay, so in order to compute the Z transform, the first transform is straightforward. 1 over 1 minus a Z inverse mod Z greater than a. Okay, the second one, I would like to just take a minute to do that computation, but let's just look at the example that we are working with. Okay, so we will come back to we'll complete this. So I will put it here, page number 21. So this is to be completed. We'll come back to this in a moment. Completed. Okay. You should definitely remind me to make sure that we do that. Okay, second property that we have in terms of the expression. If I delay the input x of n minus n naught by n naught units of time, then the z transform gets delayed. Remember, in the DTFT it was a phase term. In this case you have z power minus n naught, whatever was n naught now goes as an exponent here and multiplied by x of z. Let's just quickly verify that this is indeed the result, and then after that we'll be able to apply it. So we are so this is the second property that we are looking at. It is called the time shift property. Time shift property. Okay. So we are given that x of n has got a z transform which has got x of z, and this is ROC. Okay, there is a region of convergence. We will call that as R subscript x. And we have defined a new sequence x1 of n, which is x of n minus n naught. It's a time shifted version. N naught can be positive or negative, doesn't matter. So we are looking to compute x1 of z. This will be summation n equal to minus infinity to infinity, x1 of n z power minus n, substitute for x1 of n equal to minus infinity to infinity, x of n minus n naught z minus n. Okay, I will do a simple change of variable where L will be equal to n minus n naught. So this is now equal to L equal to minus infinity to infinity, x of L z power minus n is equal to L plus n naught. Okay, so then you can simplify this as z power minus n naught summation L equal to minus infinity to infinity, x of L z power minus L, and this is nothing but the expression of x of z. So we can now say that x1 of n has got a z transform which is given by z power minus n naught x of z. So what about the ROC? The ROC, x of z is still the same, right? So therefore the poles are the same. So therefore this is going to be R of x, except that you now have a term z power minus n naught sitting in front. Okay, so if n naught is positive, that means it is a delay. You're causing a delay in the sequence. So if n naught is positive, then z equal to 0 has to be excluded from the region of convergence. Excluded from ROC. If n naught is negative, then minus n naught will be positive, and therefore z equal to infinity is excluded. Okay, so it is the same ROC, except that you may have to exclude one of the two points. So notice it is R of x, same region of convergence, except for the possible the conditions on z equal to 0 and z equal to infinity. So that is the second expression that we have. Okay, so where do we apply this result? This result is actually a very powerful result. So supposing I were to tell you that x of z is of the form a plus b z inverse divided by 1 minus alpha Z inverse. Okay, and we are given the ROC mod Z greater than alpha. That means it's a right-sided sequence is the expression that we are given for us. So how do we deal with this? This is actually a very useful application of the shift property and the linearity property. So I'm going to write this as A divided by 1 minus alpha Z inverse plus B times Z inverse into 1 over 1 minus alpha Z inverse. Okay, so the first term says a scale factor A into 1 over 1 minus alpha Z inverse. So therefore x of n from the first term will be alpha raised to the power n u of n. Okay, alpha raised to the power n u of n. The second term, scale factor of B, you will get alpha power n u of n, but remember there is a Z inverse. What does Z inverse times x of n do? It shifts the input sequence by 1 unit of time. So what will this be? This will be alpha raised to the power n minus 1 u of n minus 1. So basically Z inverse h of z shifts the input sequence by 1 unit of time. So n minus 1 u of n minus 1. Okay, so this is a very powerful tool where you are able to use the property of linearity and the property of shift to be able to apply the result of interest to us. Okay, so now remember we said that we're going to complete this in the following manner. So what I would like you to do is to look at the application of the delay part, and then look at how to do that. So if you do x of the x delayed by n units of time, then you can write down the second term by using the property that we have just now described. This can be written as a power n z power minus n divided by 1 minus a z inverse. Okay, ROC will be mod z greater than a, still the same thing. So what we can do is we can combine these two terms, 1 minus a power n z power minus n divided by 1 minus a z inverse. So I will now strike out the fact that this has been now completed, and remember this is a ROC with pole zero cancellation, and because of that pole zero cancellation, we then have ROC will be entire z plane, and because it has got negative powers of z, that is the expression that we have, z equal to 0 is, has to be excluded, excluding z equal to 0. So the ROC is mod z greater than 0. Okay. So what we find is that the property of time shifting, property of linearity are both extremely useful. We are able to use them in a powerful manner. So we have ticked off those. The third one is called a multiplication by exponential. This property, so the second one is a shift property. Okay, so this is let me write it on this side. This is a shift property. The first one was the property of linearity.